Hello, everybody, and welcome back for our third lesson on kinetics, where today we're going to be talking about integrated rate laws. If you've taken calculus, that word integrated should sound familiar from integrals. And if you haven't taken calculus, it doesn't matter because you don't need to know how to do it. Okay, so up until this point, we have been working with what are called differential rate laws. All right, and it's okay that you don't really understand the word differential if you don't, but just know that these rate laws are different than integrated rate laws. So we have been working with ones that look like this. Rate equals the rate constant times concentration of the reactants raised to their order. These relate concentrations to rate. Okay, so we've been given data like the table here, and we've been asked to find the rate law. And we know that it's a differential rate law question when we're given concentrations and rate. Okay, now why am I pointing this out? Because integrated rate laws are different and we're going to be given different data. That's because integrated rate laws actually relate the concentration of reactants to time. So see, we can immediately tell that we have an integrated rate law question rather than a differential rate law question because we're given time and concentration. Now, we will only do first, second, and zero order integrated rate law questions with one reactant. So we will only be dealing with one reactant if we're having to use an integrated rate law. Now, these are the same, like the rate constant is the same at the same temperature for a reaction. It doesn't change, okay? These are just two ways of expressing the rates. We can do it in a differential rate law or we can do it in an integrated rate law. Differential if we're given rates, integrated if we're given time. So within these integrated rate law equations, we're going to have some variables. We're going to have T, which is time, K, which is still our rate constant, the same thing as before, concentration of A after an amount of time, that's what that little t, and remember brackets means concentration of, and then this little like subscript of 0 is the initial concentration of A. So those are what our variables mean. So let's start with our first order reaction. So remember, I mentioned before that we are only going to be dealing with one reactant. So we are never going to have multiple reactants if we are doing integrated rate laws. So for a first order reaction with one reactant, the differential rate law, the way we've been writing it, would be rate equals K times concentration of A. So the 1, because it's first order. The integrated rate law, as we mentioned, relates the concentration to time. And what I'm going to do is I'm going to hop down here really quick to show you where this comes from. So in integrated rate laws, we are going to graph the data. So for first order, the graph that produces a straight line is the natural log of the concentration versus time. And it gives us a straight line with a slope equal to negative K. Now, why is the slope negative? Well, that's because as the concentration is decreasing over the course of the reaction, so of course our points are going to be going down, so we're going to have a negative slope. When we take the negative log of those points to graph it for a first order reaction, those are also going to be decreasing, and so we have a negative slope. And K is not negative, so that's why my slope equals negative K, so that I get rid of that negative and I can get my rate constant from my graph. So we all know that the equation of a line is y equals mx plus b. So if we relate this to our integrated rate law for first order graph, the natural log of the concentration of A after time is my y. My slope, as we mentioned a second ago, is negative K. Of course, my x is time. and then my y-intercept is the natural log of A initially. So what the integrated rate law does is it gives us a graph with an equation of a line, and it will allow us to then, once we have this equation, we can calculate the concentration for any amount of time once we have our integrated rate law. So something else to point out is that my units for my slope for first order are going to be 1/seconds. So that's important to note because sometimes we may just be given the K, and because we're given the K, we know the order of the reaction. Okay? So the major things that we need to take away from this is that for a first order reaction, the integrated rate law grabs the natural log of the concentration to give me a straight line versus time. And this is our equation. Now, it is given on your reference sheet like this, but those are the exact same thing. It just has this natural log of concentration of A initially moved to the left-hand side. They're the exact same thing. So let's look at an example. So we're given this data of the decomposition of hydrogen peroxide. I know immediately that it's an integrated rate law question because I'm given time, not rates. I'm given time and concentration. Now, this one goes ahead and this table gives me the natural log as well because I'm graphing time versus natural log to see if this is first order. Well, it is first order because I have a linear line when I graphed time versus natural log of the concentration. So this is first order. So think about it. Before, with our differential equations, we were checking how did the concentration change affect the rate change. That's how we determine the order. With integrated rate laws, we graph it to determine the order. So the graph is linear for time versus natural log, so this is a first order reaction. Now, I can use this to also determine the rate constant because we remember that the rate is equal to, whoops, not the rate, what am I saying? Slope. Goodness gracious. Is equal to negative K. So how do I calculate slope? Now, if you plot this in your calculator, you can absolutely use the linear regression to find your slope. Or we can kind of do it the old-fashioned way, and we know that slope is equal to the change in y over the change in x, y2 minus y1, x2 minus x1. Now, the biggest mistake that students make in finding the rate constant from this data is they plug in concentration as their y value. But for a first order graph, our y-axis isn't concentration, it's natural log. So you have to remember that this is my y and this is my x, okay? So I'm going to do negative 2.772 minus 0. You can use any points. I just always use the last and the first as a habit. That's just how I've always done it. But you should get the same value no matter which 2 points you use, as long as you're consistent. And then I'm going to do my change in x, so 24 minus 0. So when I calculate that, I'm going to get, if I can find my little piece of paper, I'm going to get negative 0.1155. Now remember, slope equals negative k, so then k equals 0.116 1/seconds, because this is first order, and so the units are 1/seconds. So I used this data to also calculate my rate constant. Okay, so now let's look at second order. So for a second order reaction with one reactant, my differential rate law would be rate equals K times the concentration of A squared to indicate the second order. For second order, my graph that produces a straight line is 1 over concentration versus time, or the inverse of concentration versus time. That gives me a slope equal to K. Why is it not negative this time? Because I took the inverse. So if my concentration was going down, when I took the inverse, it's going to be going up, okay? And so just like with our last graph, because we graph it, we can get an equation of a line, which gives me that the integrated rate law is equal to the inverse of the concentration of A over time, 1 over the concentration of A after time equals KT plus 1 over the initial concentration of A. My units for second order are 1 over molarity seconds, okay? So big takeaway here, this is my equation, and for second order, my graph is 1 over concentration. It gives me the straight line. So let's look at this example. So I'm given data for a reaction involving C4H6. So here's my concentration and time. So I know this is integrated rate law because I'm given time and concentration, okay? So this time I graphed the natural log as well as the inverse. So this is a first order plot and this is a second order plot. How do I know which order? I literally look and see, well, this plot is extremely linear, this one isn't, so this is a second order reaction. Now, I can calculate the rate constant by doing change in X over change in Y. So I'm going to do my last 2 points. Remember, my second order is the graph, so I'm finding the slope for this graph, so I have to do the 1 over. Now, this data was really nice because it gave me the values of the inverse, but sometimes they might not, and so you might have to take the concentration data and calculate the inverse for each of your points. So I'm going to do change in Y, 481 minus 100 over my change in X, so 6200 minus 0. And I get that K equals 0.0613, 1 over molarity seconds, because that's my unit for a second order reaction. So once I determine that it's second order, I can calculate the slope for the rate constant. This time there was no negative. I didn't have to worry about that because it's a positive slope. Last but not least, we have our zero order reaction. So in a zero order reaction with one reactant, rate just equals the rate constant for my differential rate law. I have no reactant concentration because it's raised to the 0, which means it's 1, so we don't include that in the differential rate law. So for zero order, my graph is simply of time versus the concentration, and my slope is equal to negative K. So again, I have my equation of a line here, which gives me my differential rate law, or excuse me, my integrated rate law equation. My units for zero order are molarity over second. If we ever forget this, again, you can just calculate it from the differential rate law. Rate is equal to molarity over second equals K, so then K's units are molarity over seconds. So for zero order, again, it is the time versus concentration that will give me my straight linear line. We can see that here. So we're given two, I don't have the data. However, it was data for the decomposition of silicon dioxide and the decomposition of tungsten. Both of them are graphed time versus concentration. We're given a linear line for tungsten. So we know that this is zero order. This is not zero order. We would have to try graphing the data versus the natural log of the concentration and then versus the inverse to see if it was first or second order. Okay, so let's look at an example. So we're given the following data: time versus the concentration of dinitrogen pentoxide. Okay, so immediately, if this were a test or a quiz and you were given this data, you would know that you have to use integrated rate laws instead of differential rate laws because I'm not given concentration versus rate. If I have the rate, I can do the initial rates method to determine my order. I'm not given rate here, so that's not going to work. So I have to do integrated rate law because I have time and concentration. Okay? Now, AP chemistry is not testing your ability to graph. Okay? Now, for a practice question, maybe you aren't given the graphs and you would need to plug it into your calculator. But on a test or quiz, you will be given the graphs and you will just need to be able to interpret them. So I have graphed this data for you. And remember, for a zero order plot, it's the concentration. For a first order plot, it's the natural log. And for a second order plot, it's the inverse. I look at these three graphs and I can very easily see that the most linear is the natural log plot. So then that tells me that this is first order. Now, because I'm given my equation, I can just look at the equation and I know that K is equal to the slope 0.351. It's first order, so 1 over, I think I was given seconds before. Okay, so that's all. If I was not given the equation of the line, I could find K with the slope by doing change in Y over change in X. Okay, so if you are still listening at this point, I would love for you to send me a joke in Remind to make me laugh. If you send me a joke and you make me laugh, I'll give you an extra credit point. Okay, so last thing for this topic of integrated rate laws. So because integrated rate laws relate time to concentration, we can use them to analyze half-life. Half-life is something that you've seen before. You saw it in regular chemistry, you've looked at it in math class because it's an example of exponential change, but it's the time required for half of something to be consumed, or to decay, or whatever. And if we're thinking of this in terms of our integrated rate laws, we can change our variables to be the concentration of A after half-life equals 1/2 the concentration, right? Because half-life is how long it takes to get to 1/2. So for first order, if I plug in these variables of half-life and 1/2 the initial concentration, I do all this simplifying, which you really don't need to worry about because you're given this on your reference sheet. So for first order, the half-life of a first order reaction is equal to 0.693 over K. So you can look here and see how we simplify to that. So the half-life is equal to the natural log of the initial concentration over half the concentration times 1 over K. Simplify that. Well, anything divided by half of itself is going to be 2, so we get the natural log of 2 over K, and that's simplified to 0.693 over K. That's what's given on your reference sheet. So what does this tell me? One thing it tells me is that the half-life of a first-order reaction does not depend on concentration. So for a first-order reaction, the only thing that dictates the half-life is the rate constant. So sometimes you might be given a set of data, and you may be able to look and see that the half-life stays constant. So to go from 100 to 50 is 2 days. 50 to 25 is 2 days. 25 to 12.5, 2 days. If the rate, the half-life stays consistent, it's a first-order reaction. So the larger the rate constant, the shorter the half-life. The smaller the rate constant, the longer the half-life. And that makes sense. The other thing is because it doesn't depend on concentration, if we know the half-life, we can calculate the rate constant of a reaction. But this only works for first order, that we can use the half-life to calculate the rate constant. And here's an example of this here. So we're given the decomposition of hydrogen peroxide, and they tell us the half-life is 2.16 times 10 to the 4th seconds. So what I can do is use this half-life to calculate my rate constant. So this is just another way to determine the rate constant of a first order reaction. But again, this only works for first order because we see when we calculate or simplify the expression for half-life of a second order reaction, we have half-life equals 1 over K times the initial concentration. So now half-life does depend on the concentration, and it's inversely proportional. So the half-life of something decreases as the initial concentration increases. So then that means that as the reaction proceeds, the half-life is actually going to get longer and longer. So if we see a half-life getting longer as the reaction proceeds, we know that we have a second order reaction. Finally, zero order is half-life equals the initial concentration over 2 times K. So again, half-life does depend on concentration, and this time it's directly proportional. So half-life is actually going to decrease as the reaction proceeds because the concentration decreases. So half-life increases as initial concentration increases. So if we see a reaction where the half-life is getting shorter and shorter as the reaction proceeds, then we have a zero order reaction. Now, you are only given the half-life equation on your reference sheet for first order. So typically speaking, on a test type question, you're only going to have to do half-lives with first order. Okay? So this first question, what is the half-life for the first order decay of phosphorus 32? They give me the rate constant. So I look at my equation and, running rate. Half-life, or time 1/2, is equal to 0.693 over 4.85 times 10 to the negative 2. So that's days to the negative 1 is the unit, which makes sense because that pops it up in the numerator. So I'm going to do 0.693 divided by 4.85 to the negative 2, and I get that the half-life is 14.3 days. Easy enough. Second one, the first order radioactive decay of iodine 131 has a half-life of 5 days. What's the rate constant? So this time I know that my half-life is 5 days, and since this is first order and the rate constant doesn't depend on concentration, I can use the half-life to calculate K. So K is equal to 0.13, sorry, I don't have room because of the little floating head of me. K equals 0.139 and 1 over days. It's first order, so the rate constant is 1 over time. Okay, so here is a summary. This chart is phenomenal. You can find them all over the internet, or you can use this one to study. But it is a summary of everything with integrated rate laws. So 0 first and second order, the first thing you're given is this is the differential rate law, or like our normal expression that we started the unit writing. We're given the units of K. Then you're given the integrated rate law equation, the plot needed to tell us if it is that order, the relationship of K to the slope, and then you're also given the half-life equations. So this is a great chart to print out and to have it to use and to study. All right, and really quickly, I just wanted to show you what you're given on your equation sheet for kinetics. So I pointed this out in the notes. So this is the half-life for first order. which means typically if you need to do any half-life calculations, they'll be first order. And then you're given the first order integrated rate law, the second order integrated rate law. You're not given zero order, but if you need it, zero order is just the concentration. So you just take out these inverses and that would be zero order. Okay. And then of course they define the variables, but I don't even think you need that. But I just wanted to point out what you are given on your equation sheet. Thanks for listening. See you next time.